Alrighty, good. Well, it's good morning for me, everybody. Probably good afternoon by the time you get around to watching this. It's me, Victor. I'm here to go over section 1.2 with you guys in case we didn't have time to do it in class today. So when I'm looking over this, the first thing that I see is we're going back to equations, but this time we're talking about function notation. And function notation is going to be kind of integral to understanding the way that we're going to look at math as we move forward. Now, it's very similar when I have an f of x, it's going to be very similar to what a y represented in previous equations. For example, we were used to seeing y equals 2x plus 1 or something like that. And instead of this y, I'm going to see an f of x equals 2x plus 1. And it's going to function, just a joke, it's going to function pretty much the same thing as that y, except there's going to be some slight differences in how we just show what's going on. So for example, when I look at these example problems here, this is asking me to find f of 5. And you might be thinking, what is that, f times 5? But that's not f times 5. What that means is previously we would have f of x, or in this case it's f of n. And so what this is asking us to do is wherever we see an n in f of n, so f of n is 8n minus 3, we are instead going to write a 5. So this would be 8n minus 3, but because this 5 right here is where the n is supposed to be, that tells me that the n here should be 5. So when I say f of 5, what I mean is 8 times 5 minus 3. And then I just evaluate from there. So I know that 8 times 5 is 40 minus 3, and that's going to be 37. So I know that f of 5 equals 37. So that's how I'm going to solve all of these problems. Like for g of 5, I'm going to do the same thing. I have 3n minus 10, but I know that the n is actually 5, so this n needs to be the number that's in that parentheses. So this becomes 3 times 5 minus 10, or 15 minus 10, or what is that? 5. F of 5, or I'm sorry, g of 5 is 5. And we do the same thing for all of these. For this, I do a negative 4 for that n. I do a negative 4 for that n, and et cetera, et cetera. And so you can see that we're just going to be comparing how these functions behave based on what numbers we plug in for n. And it's also actually interesting to note that this number here, this n number, we could represent it as an ordered pair. So this n, previously I would say it would be an x. This example uses an n. But I could put that in for my x coordinate, and then my output, in this case 37, would be my y coordinate. And I could put it like that, so that this is x comma y. So this is a point on the Cartesian plane. In this case, it's 5, so I go over 1, 2, 3, 4, 5, and then I go up 37, which is a lot. It's like up here or something. Just a little bit of additional information. For the next section, we're continuing our work looking at patterns. And it's a little bit faded on here. Let me see if I can zoom in so it's a little bit more clear. Yeah, it's a little bit faded on my copy here. But it's pretty much what we're going to be looking for is we're going to be looking for a pattern of change. Now, one of the ways we can look for a pattern of change is we can look to see what the difference, look for difference from one term to the next. So if I go from the second term to the first term, what is the difference there? Remember, difference is just a fancy mathematical way of saying subtract. Okay, it's just a fancy way of saying subtract. So if I do 4 minus 2, because that's my second term, minus my first term, except I'm going this way, 4 minus 2, I see that my difference is 2. And sure enough, I can see that 2 plus 2 is 4. Well, is that the same here? Can I do 4 plus 2 equals 8? I can't. 4 plus 2 is 6. So I know that that's not actually what's going on here. So if it's not difference, what could it be? Well, in that case, we have to assume that we're not adding the same number each time. We're multiplying by a number. Okay, so now we're going to look for the ratio, okay, which is a fancy way of saying divide. Okay, so I'm going to try this again. This time, I'm going to do 4 divided by 2, which is 2, okay? Yeah, 2 times 2 is 4, that's true. So let me try a different step. Let me try 8 divided by 4. 8 divided by 4 is also 2. Oh, excellent. So I've confirmed that each time what I'm doing to get from one step to another is I'm multiplying by 2. And sure enough, 8 times 2 is 16. 16 times 2 is 32. So to complete this, I just have to keep multiplying by 2. This becomes 64. This becomes 128. This becomes, what is that, 256. I knew that. Boom. And so that's how we do it. So you have to look for both. You have to look to see if there's a difference, to see if we're adding the same number each time, or you need to look for a ratio to see if we're multiplying each time. And they're going to be different. Some of them will be multiplication, some of them will be division. Doesn't matter. We just need to figure out what we're doing. Alrighty, let's go to the next section here. Okie dokie. Here we go. This is kind of the same sort of thing, except we're doing a visual representation, and so we have to see what our pattern is. And when I go from step 1 to step 2, I see that I've added here, here, and here. And then when I go to step 3, I see that this is the same as step 2, except I've added here, here, and here. And so for step 4, I can imagine it's going to be the same. So I'm going to have 1 block, 2 block, 3 block, 4 block, 5 block, 6 block, 7 block, just like that. But if the pattern were to continue, that would mean I add a block here, I add a block here, and I add a block here. And you can see that each time we're adding 3, right? Add 3, add 3, add 3. So I'll add 3 here. So that's a whole lot of blocks. Let me do it the lazy Victor way. So there's 1 block. Boop, boop. Beep, bop. Scooby-Doo. And then I get to add my blocks on the end, like that-arino. Okay? So that's what's going on there. So, final section? Yeah, no, penultimate section. That means next to last section. So what we're looking at here is to note what's going on here. The students in the class were asked to find the number of tiles in a figure by describing how they saw the pattern of tiles change at each step. Match each student's way of describing the patterns with the appropriate equation below. Okay, so what we have to do is, this is going to be that part where we're connecting how quantities are defined, and we're going to be interpreting expressions. So when I look at this, Dan explains that the middle tower, so we're talking about this, the middle tower is always the same as the step number. He also pointed out that the 2 arms on each side of the tower contain 1 less block than the step number. Okay, so we have the step number is the center tower. So we see this is 2 times the step number, and he doesn't really say anything about 2 times the step number. This is step number minus 1, and it doesn't really say that. 3 times the step number. It doesn't really say 3 times the step number. Oh, but here's one where it's just the step number by itself. So Dan explains that the middle tower. So this represents the middle tower. And then he also points out that the 2 arms on each side, the 2 arms on each side contain 1 less block than the step number. So 2 right here is the arms. There's the step number, but there's 1 less block than the step number. And so we would say that this mathematical way of talking about our arms here is what Dan is talking about. And so you'll go through 15 and 16 and try to figure out exactly what's going on there. All right, let's turn the page. Turn the page for one final bit. We are going to be talking about exponents. Uh-oh, looks like my screen froze. Let me restart it. There we go. That happens sometimes. Luckily I caught it instead of recording a whole video with a frozen screen. So it says write the expression as an exponent. Okay? So an exponent means we're multiplying it by itself that many times. So when I see 6 times 6, that's 2. Times 6, that's 3. Times 6, that's 4. Times 6, that's 5. that means I'm doing 6 to the 5th power. Okay? I'll do one more. So I have 4 times 4 times 4, so that's 4 to the 3rd power. Likewise, this is the opposite way of doing it. If I have 7 to the 1st power, that means I have a 7 by itself. If I have 3 squared, or 3 to the 2nd power, that's 3 times 3, which we know is 9. 5 to the 3rd power, I'm going to do one more. 5 to the 3rd power, 5 cubed, is 5 times 5 times 5, or 125. Okay? And that's how you do all of these. This is a quick overview to help you with your homework tonight. Feel free to ask me more questions tomorrow. If some of these needed a little bit more explaining than what I did today, make sure you talk to the people at your table as well. Work together as a team to be able to get this stuff done. And I will see you tomorrow.